It's actually far more serious for linear. Yeah. I haven't looked at the number of views, so I have no idea. You know, Sharon has watched it 6 times. Like more than one person besides Sharon has watched it. What exactly happened?
We all got together at Domino's and watched it.
Oh, that's what I told you before. So, this is lecture 12, I suppose. Which is probably on the quadratic integers. Which is not like that thing, it's a class of things. We're going to look at a couple of examples. First of all, let's see here. First of all, I'm going to show you an argument which is slightly unjustified. So basically what I'm doing, I'm about to do right here is somewhat in line with what happened in chapter 1. In chapter 1, at the very end, we derived the Euclid's parametric formulas for the primitive triples by factoring x squared plus 1. We're like, if you got a solution of x squared plus y squared equals z squared, then x squared plus y squared factors is like x minus iy times x plus iy. But if that's equal to z squared, that means you've got a product of things equal to a square. But if those things are relatively prime, it must be that both of those things are also squares. And then consequently, by unique prime factorization, we're able to say both of those factors are in fact squares. And from that, we derive Euclid's parametric formulas. We're about to do almost the same thing for, I think this is Batchett's equation. Forget. But here it is. So let's look at y cubed equals x squared plus 2. As usual, we're looking for integer solutions here. I mean, that's our goal, is to find some integer solutions. All right, so basically what do you do? I mean, how can you factor that? Let me rewrite it. This is x squared minus a minus 2 squared, right? Well, no, that's not right. Minus the square root of minus 2 squared, right? So I can write this as x minus the square root of minus 2 times x plus the square root of minus 2. We can make a little claim. X minus the square root of minus 2 and x plus the square root of minus 2 are relatively prime. I mean, if we talk about z join the square root of minus 1, we can just as well talk about z join the square root of minus 2. I mean, just to link, I mean, the notation's a little bit, just slightly off-putting. So we had zi before, right? This is like a lot more obviously the same thing if you look at this instead of z is joining the square root of minus 1, right? I mean, so I'm kind of doing the same thing, but now with the square root of minus 2 instead of the square root of minus 1, right? That's roughly the idea. But if this factor and that factor, right, if those are relatively prime and they're equal to what? A cube, what does that say about these? I mean, let's just go back to the basics, for example. If I've got, let's see here, if I can think of an example. Oh, goodness gracious. Oh, they're so big. Processing, just a second here. 216 is what? I have another chicken out here for. Okay. What is this? This is 6 times 6 times 6, isn't it? Right. But this is also equal to what? 27 times what? Times 8. You notice that the greatest common divisor of 8 and 27 is what? 1, right? It's a relatively prime. And it's no accident that this is 3 cubed and this is 2 cubed, right? Now, if you don't have that the things which are forming the cube are relatively prime, there's really no assurance that it's going to work, right? I mean, if I don't have that the product, the factors are relatively prime, then I could have some of the things making the cube in one and some of the things making the cube in the other. There could be a shared divisor of both. But if they're relatively prime, then we should be sure that each one of these is a cube, right? So what does that mean? That means that x minus the square root of 2, minus 2 rather, should be equal to something like a plus b times the square root of minus 2 cubed, right? I mean, that's what it means for it to be a cube. It's the cube of something else in z adjoint square root of minus 2. And so then you can do algebra, right? You can multiply this out, what do you get? A cubed plus 3 a squared b root minus 2 plus 3a b root minus 2 quantity squared plus b root minus 2 cubed. So what I did there was just the usual binomial coefficients, 1, 3, 3, 1 for the cube. What does that give me? That gives me a cubed. That gives me a minus 2, right? So minus 6ab plus parentheses 3a squared b. And this gives me minus 2b cubed square root of minus 2. But the coefficients here have to match up, right? Like whatever's here has to match this x, right? And perhaps more instructive than whatever's here has to match this minus 1, which is right there, right? So we get two equations here. What are the two equations we get? We get your x is equal to a cubed minus 6ab. Okay, that's not especially enlightening. But the other one is pretty awesome because the other one says, I'm gonna solve it for 1. 1 is equal to 2b cubed. I absorb the minus 3a squared b. All right, now that we can factor out of b. Let's see here. So I'm going to factor b out. What do we get? 2b squared. I'm going to pull the b out this way for whatever reason. Minus 3a squared times b. So what does this say? This says, in particular, this says b is a divisor of what? It says b is a divisor of 1, right? See that? So what are your choices? If b is an integer, what are the divisors of 1 and z? Right. So b is plus or minus 1. Now, so then I think the easiest thing to do is just break into cases, right? If b is equal to 1, what do you get? 1 is equal to what? 2 minus 3a squared, which tells me what? 3a squared is equal to 1, right? That forces a equal to what, since, oh, wait a minute. I mean, we can solve this if we step outside the integers for a second here, right? Like, you know the solution is plus or minus 1 over root 3. In other words, there is no integer solution, right? what's the other case? Equals minus 1, right? Then I get 1 is equal to 2 minus 3a squared times minus 1, right? Which then tells me that, what does it tell me? Take some mark? Sorry, another step, minus 1, I'm an idiot. 2 minus 3a squared. Okay, algebra. So minus 3 is equal to minus 3a squared. So 1 is equal to a squared. So a is equal to plus or minus 1. Those are both integers. So we find two solutions, right? So either a equals 1, b equals minus 1, or a equals minus 1, b equals minus 1. Those are the solutions to the second equation here, right? Then what do we do? Plug them back in, right? So, let's see here. So therefore, we have x is equal to, let's see here, a cubed plus 6a, which is either equal to what? If a is equal to 1, it's what? It's 7. If a is equal to minus 1, what do we got? Minus 7? Yeah. And what's y equal to? Oh. I guess y cubed is what? So y is equal to the cube root of x squared plus 2, apparently, right? Which is what? Yeah, cube root of
51.
I did something wrong here. That was supposed to be 5.
A cube. What is that?
What's that?
Where did you get x equals a squared, a cubed plus 6a? I think it should be minus.
A cube minus 6ab.
Or 6a.
Well, b was minus 1, right?
Oh, okay. And when you factored out a plus b squared root of minus 2 cubed, I think you forgot a b squared.
Where? What?
Okay, the second line.
Oh, where?
You have b squared minus 2 and all this squared.
Oh, that's a b squared. Yes, thank you. That's exactly it right there. See, when I square this, that gave me minus 2 times 3, which is the minus 6. But I should also have a b squared. Thank you. That is the error. Aha. It's like, this isn't a cube. I was plugging it in, I got 23, which is not a cube, right? But if you put the b squared, we get minus here, right? Because minus 1 squared is just 1, so I get a cubed minus 6a, which ends up being what? For a equals to 1, it's what? It's minus 5.
Mm-hmm.
And for a equals to minus 1, it's what? It's 5. So we're interested in this solution mostly, all right? So that's 25 plus 2, which as we know is 27. And of course, the cube root of 27 is 3. So returning back to the start of all this, we find solution x equals to plus or minus 5, and y equals to 3. And I think there's some chance that you might have just seen that from guessing, right? There's some chance of that. So this was known to Fermat in 1657, he claimed that there was no other solution in the natural numbers. The proof that I just gave you here is essentially offered by Euler in the 18th century. Right? Again, you see, like, using these non-real, sketchy algebraic numbers gives us this way to derive things, which, I mean, Gauss was apparently very suspicious of these kinds of arguments at the outset because when he did his master work in 1801, he didn't use these sorts of things. So like this predates Gauss's sort of awesome work when he was 19 years old or so. What, 30, 40 years before that, people like Lagrange and Euler were kind of freestyling, using stuff like this without quite, there's some claims here that they haven't really fleshed out entirely. And in fact, some of these things stop being true if you look at other extensions. Like the unique prime factorization. We're going to see if you adjoin the square root of -3 today, it fails. Well, we don't have to wait for that. Let me show you. Why does unique prime factorization fail for z adjoin root 3? Square root of -3. Prime factorization fails. So before I get into some of the nitty-gritty on why this calculation was okay, let me just take a second to warn you about how it breaks down when you go to like even the next logical case like this, right? Maybe you just expect this helps you to look at things with like a 3 in it, Maybe if I replace the 2 with a 3, I could solve that problem by just looking at these numbers and factoring in there, right? But here's the thing. If you look at the number 4, of course you can write 4 as 2 times 2, right? But how else can you write it? True.
1 minus square root of -3 is 1 plus square root of -3.
1 minus the square root of, yes, it's the square root of this squared. Just write it down. So you see you get minus from the plus minus, and you get another minus from the square of these guys, right? I mean, there is a unique prime factorization in the integers, after all. That's the fundamental theorem of arithmetic, right? This is it for z. Up to reordering, that's all you got. Oh, you got the plus or minus right. I could write -2 times -2. We don't know whatever. We for some reason don't care about that. But this, if you're allowed to work in this happy-go-lucky place, z adjoin square root of -3, all of a sudden you got this as well. And these are, you can prove, you can show that both 2 and 1 minus square root of -3, plus or minus, you can show that these in fact are prime. They're sort of, let's say, analogs of Gaussian primes in this cell. I wouldn't call them Gaussian primes here because this is not the Gaussian integers, right?
Shouldn't that be positive? Square root of positive?
What? No. If you multiply this out, what do I get? The cross terms cancel, right? And I'm left with like 1 minus the square root of -3 squared, right? Which is 1 minus a -3, which is 1. So yeah, the square root of -3 is an important feature to that factorization. You don't get it if you just adjoin root 3. But so in fact, you can show both 2 and 1 plus or minus the square root of -3. These are primes in this new extension of the integers. So there's not a unique prime factorization of 4, but that's really bad because everything we do with Euclid's algorithm and all that stuff rests on the unique prime factorization, right? Like the prime divisor property, all the things we know and love, all of our arguments that led to being able to say, if you've got a cube equal to a product of relatively prime pairs, the prime's got to be in one of these or the other, right? Because there's a unique prime factorization, and if there's a cube over here, there's got to be a cube hiding here, because there can't be something shared in common. Well, all of a sudden, what's common is ambiguous, and you can't make these kinds of arguments in here, right? So that kind of thing is what made Gauss be suspicious of this manner of argumentation, right? And like, what's the difference between z adjoin root minus 2 and z adjoin root minus 3? They all look awfully similar, but yeah, they're quite different, yeah. Sure.
Are those Gaussian primes then?
No, the Gaussian primes are, this is the Gaussian primes up here. These, you know, z adjoin the square root of minus 2, as far as I know, doesn't have a name, except z adjoin the square root of minus 2. It's kind of an annoying name, but a name. If I look at the quadratic integers, what are quadratic integers? Basically, it's just alpha in the complex numbers, such that what? Such that alpha squared plus a1 alpha plus a0 is equal to 0 for some choice of integers a1 and a0. Okay, so that's the definition of quadratic integers. There's some so-called monic meaning that the coefficient of the leading term is 1. There's a monic quadratic polynomial that the integer alpha appears as a solution for, and alpha is some complex number. That's a definition of quadratic integers, something like that. So for example, Gaussian integers are quadratic integers because like I squared plus 1 is equal to 0, right? In other words, it solves the monic polynomial equation x squared plus 1 equals to 0. Square root of minus 2, what is that? That solves this equation, x squared plus 2 equals to 0, right? So it's a solution to the monic polynomial equation, x squared plus 2 equals to 0. All right. These guys, despite their malfeasance and lack of unique prime factorization, still give you a set of quadratic integers. Well, yeah, I think they do. I mean, apparently my definition allows it, right? These guys appear as solutions to what? X squared plus 3 equals to 0. They're integers. They're solutions to that monic polynomial. So there's this like huge ocean of examples that you can think about. Quadratic integers, right? And there's lots of things in here. There's the Gaussian integers, right? There's these guys, and so forth and so on. All right, so did you like my setup for the video? I spent like a whole $7 on that whiteboard. I'm going to try writing on that thing. I'm not sure how that's going to work out, but I had to kick the kids out of the garage. They're like, we'll be quiet. We'll just ride our bikes around you. No. No. Leave. All right. I'm on page 2. I've got 9 to go. I'm just kidding. I'm trying to go slow through the part that I should go through slow through. So the division property. So let's division property. Now, if you watch the video, what the argument that I'm about to show you is, man, it's almost verbatim the one I gave you for the Gaussian integers. Which, by the way, you might notice, not quite the argument which Stillwell gives. And I'm not saying Stillwell's argument is wrong. I'm just saying I can't quite latch onto it yet. So if you look at this is like a lattice of points, right? And in the complex plane, it looks something like, let's just draw some. Usually if I draw that many, it gives me a sense of what's going on. So I'll start with 0, right? So what is this set? I mean, this set of quadratic integers has the form a plus b square root of minus 2, such that a and b are integers. Now, I grow weary of this notation. Like for me, I do a lot better if I think about this as a plus I times, well, b times I root 2. So here, that is helpful because it's just I mean, there's an I there. That's the square root of minus 1, right? I mean, it's a complex number. So every once in a while, I will laugh over to this notation. I try not to too much because it still doesn't. But okay, so what do we got? 1 minus 1, right? You guys with me there, graphically? What's up here? What's this guy?
Square root minus 2.
I times, yeah, I root 2, or square root minus 2 if you like. I'm going to use I because it's easier for me to write than square root minus 2 for some reason. I mean, square root of minus 2 looks messy to me. I don't know. But down here, you've got minus I times the square root of 2. How about up here? What's this one? This upper right point.
1 plus I square root of 2.
Right, 1 plus I root 2. How about this guy?
I square root of 2 minus 1.
Yeah, minus, you say minus 1?
Minus 1 plus.
Yeah.
Plus I root 2. Can you read?
Yeah, I just swapped it.
And then this one's down here is minus 1 minus I root 2. And this one over here will be 1 minus I root 2. Okay. Once you get started, it's pretty easy to see how these points are distributed, right? So in your mind's eye, imagine an arbitrary grid, an arbitrary square somewhere in the complex plane. What's it kind of look like? If I make the lower corner, let's say m plus I squared m plus n I root 2, right? What are the other, if that's the lower corner, what are the other guys? Corners here, like what's this one? M plus 1 plus m I root 2, right? So you just shift 1 over in the real part. On the flip side, to go vertical, you shift 1 up in the imaginary part, right? So this is m plus n plus 1 I root 2. And then finally, the upper right-hand corner, you shift the imaginary part, imaginary coefficient, and the real coefficient, both by 1 unit, right? So you get m plus 1 plus n plus 1 I root 2, right? So that's what a typical, that's what a typical square, not square, is this a square? It's not a square, is it? What's, let's see here. I mean, the side length here is what? This length is what? Square root of 2, right? Whereas the horizontal is what? 1, right? You guys with us? I'm trying to go slow enough so you can see the argument here. It's really simple. It's really simple. So I want to find the division property, right? Which basically means I want to be able to describe the quotient of 2. If it's okay with you guys, I'm going to erase this grid now and work over here, okay? Well, even if it's not okay, I'm still going to do it. So let's let's say a plus b times square root of minus 2 and c plus b times square root of minus 2 the elements of the adjoin root minus 2, right? And I want to look at, let's see here, how about c, and I need to get these names. Let's call this one z, and let's call this one w. I want to look at z over w. What's that look like? It's something like what? It's something like a plus b root minus 2 divided by c plus d root minus 2, right? Now, you had that homework problem where you worked this out for the Gaussian integers, right? You realized that if you divide them, you get another thing that's like a Gaussian rational number, so to speak, right? It's a rational combination. It's a linear combination of 1 and I with rational coefficients. Something is true here, right? Similarly, that you could write this as, say, x plus y times the square root of minus 2 in what? This would be in the rational numbers adjoin square root of minus 2, right? And even though I haven't defined that carefully, I think you know what I mean. I'm saying that x and y are rational numbers, right? Now, if you think about that, right? that's, if you think about where that you know, x plus y root minus 2, that's going to fall somewhere in the complex plane, right? So without loss of generality, let me suppose it falls somewhere in this arbitrary rectangle, right? And for purposes of my graphical convenience, I'm going to put it in the lower right corner, but that's not really sacrosanct. I mean, that's just my picture. You can, once you understand this, it's pretty easy to, so there's my x plus y square root of minus 2, right? So this allows me to choose a closest number in these quadratic integers, right? Like the closest quadratic integer here is the purple one, right? See that? And furthermore, if you focus here on the lower quadrant, I mean the lower, you know, choose the center point, and look at this subrectangle here, just for the sake of making an estimate. See that? What's this? This has what? 1/2, right? And this guy here is what? Square root of 2/2. That's a bounding box between the corner point and this rational number, right? So that means that you can see that the distance, right? The distance between x plus y square root of minus 2 and that m plus, well, it's not pretty, it's plus ni root 2. What is it? So we should give this a name or something. I don't know. Oh, fine, I'll just write. So like z over w minus, usually calls this mu. So I just call this thing mu. It's the closest quadratic integer there, right? That distance is less than what? What's the largest distance you can attain in this little rectangle?
From the center to
The diagonal, right?
Mhm.
So what would that be? 1/2 squared, right?
Mhm.
Plus the square root of 2/2 funny squared. What is that?
Plus.
Right. Which is, by the way, less than what? One, right?
Mhm.
Let me call that star. We'll use that here in just a second. Okay, so continuing here. So we chose mu in the quadratic integers, it's the adjoin square root of minus 2, for which z over w minus mu is less than 1. Now we're going to let, let's see here. Can I do this? Words. Let rho equal to, let's see here, zw minus mu. All right. Let rho equal that. So, by the way, what my goal, guys, is I'm thinking this: z over w is equal to mu plus rho over w, basically. So that's the sort of that's straight division, but we usually look at it as what zw is equal. Oh, we usually look at it as z is equal to what? Mu times w plus rho, where what? The size of the remainder is less than the size of the dividing number, right? So this is, let me put this in a, let me just put a bubble right here. This is our goal, right? This is our goal. We're trying to show this, that would be the natural division property. And I'm working my way there slowly but surely geometrically by the same argument we used for the Gaussian integers, actually. So I just said let the remainder be product of Z and W minus mu, where mu we constructed as the closest integer to the quotient of these two things looked at as a complex number. Now what do I need to show? I need to show that the size of the remainder is less than the size of the dividing number, right? So let's look at that. The magnitude of rho, that's the value in the complex plane, right? So this is actually the modulus. It's the distance, the length of rho looked at as a complex number. Complex vector, real vector. I'll shut up. This less than W is equivalent to what? That's the same as rho over W less than 1, right? But you could trade that for what? We just defined rho. Well, let's trade on. So that's the same as ZW minus mu over W less than 1, which is interchangeable with what? By the way, I know that W is not equal to 0 in all this, right? That's assumed at the outset. If W equals 0, we certainly don't want to try to find some interesting statement about Z over 0. Like, we know that's a non-starter for more basic algebra reasons. So we're assuming W is not 0 from the outset. Can you simplify that? Yep. Uh-oh. Oh, sadness. What did I do wrong? What should I make my definition, guys?
No. There's something wrong.
What happens if you solve this for rho? You get rho equals ZW minus mu? You do not. Is that a good definition for rho? No, it is not. What should I have written here? Can you guys fix it? I should have written what? I should have written Z minus what?
UW.
Correct.
That makes sense.
Now, in view of that, that makes this a lot more interesting, right? Same algebra, now we get what? Z over W minus mu less than 1. But what is that? Just underline it. What's that? No, that's, I mean, no, this is not that. Look at this. Compare star star. Just a star over here. You see, we already know that the quotient of Z and W, the distance between Z over W and the closest quadratic integer is less than 1. So we know star star is true. Consequently, we know that, in fact, yes, the remainder is so defined, right, with the proper, this correct definition of the remainder, it does in fact satisfy the needed condition that the norm of the remainder is less than the norm of the dividing number W. Consequently, division property. Right, or there you go. Now, once you have this, right, I will spare you, but you can prove, you can show that, what can you show? The next thing you want to show, to be careful, is what? So this is page 4 of my notes, but I'm going to almost skip it in here because I think we don't have time to talk about other stuff without hurrying. So You can show that the greatest common divisor of x minus the square root of minus 2 and x plus the square root of minus 2 is equal to 1. Assuming, now that's not just any x, that's assuming that x squared is equal to, well, x squared plus 2 is equal to y cubed for some x and y in the integers. So if, in other words, if x appears as we used it earlier, it is in fact, it can also be shown that, x plus or minus the square root of minus 2, those compare, there's no divisor of those except for a unit. In fact, the divisor is just 1. So that, all right, paired with the fact, once you have the division algorithm, then you can go ahead and prove the Euclidean algorithm, and then you get Bizau's identity, then you get the prime divisor property. Once you have the prime divisor property, then you get unique factorization. And once you have all those things, you can make the argument we made at the start of class. Right? So essentially, this is the linchpin. If you can prove the division property, everything else kind of just falls into the line past there, as I discussed in more detail in the Gaussian integer section. Any question about this? I just skipped page 3. It was on page 3. Uh-oh. So basically the point is relatively prime factors of a cube are themselves cubes inside the square root, inside the adjoint square root of minus 2. I guess one interesting thing to think about here for a moment before I go on is what are the units? How would you figure out what the units are in z adjoint root minus 2? I think this is a kind of an interesting question to ask in any of these weird new number systems, particularly this one. What are the units in here, right? So what is a unit? Let's go through it again. A unit is something that's a divisor of 1, right? So in other words, you have something like uv is equal to 1 for u, a unit. And here, of course, u and v would be elements of this guy, right? But what's the definition of the norm here? The norm of a plus b square root of minus 2 is by definition, right? By definition, a squared plus 2b squared. Now, I personally, I like to view this definition in terms of what's going on in the complex case, because it's much more insightful for me to look at it as this way. The norm of z, right? What is it? It's still z bar. I mean, it's just here that z is equal to a plus I b root 2, whereas z bar is a minus I b root 2. And so when you multiply these guys, you get a squared plus 2b squared, but the cross terms cancel. Once you have this, though, it's really easy to show that the norm is what? It's multiplicative, right? So norm of zw is what? Yeah, norm z, norm w, right? So once we know that, what's that say then about a unit? What's the norm of 1? 1, right? And by the way, the norm of u is what? It's greater than or equal to 0, right? So how can you have the product of 2? And it's in more to the point, it's an integer, right? That's why we work with the basic, and to me it's unnatural from the start why we're doing this. Like from a complex variables perspective, there's something really weird about what we're doing. Because I'm so used to thinking of distance in terms of the square root of the sums of the squares, right? So why don't we use square root of the sums of the squares for most arguments? I mean, I did over here, sorry. But when push comes to shove, when I'm actually talking about number theory things as opposed to, just establishing a basic property, a basic fact to establish a number theory theorem, the reason we use the square of that is because the square is itself an integer. Right? So I would say it's the modulus squared in terms of ordinary complex variables. And so that's the thing, is the norm of u, it's an integer, right? It's in z, so how can you have an integer times an integer equal to 1? There is only one choice, right? Yeah, the norm of u has to be what? Say it again. What'd you say? 1, yeah. So if u is equal to a plus ib, what are your choices? That says that a squared plus 2b squared is equal to 1, right? So certainly b is out of the question. I can't have b as plus or minus 1 here. That there's no hope, right? A and b are integers. So my only solutions are a is equal to plus or minus 1. In other words, the units in z adjoin root minus 2 are the same as the units in the ordinary integers. But this doesn't have to be, right? When we solve the same, how is this different? I think it's helpful to contrast today. Since we have 2 examples now, we can contrast. Contrast is Gaussian integers, right? Contrast to z adjoin I, what we have there. There you had something like if u is equal to, this is wrong. What should I have here? Right, I'm missing my square root of minus 2 is not optional. It's got to be there. Okay, yeah. So if I have u equals a plus ib, now I'm within my rights. That's an element of z adjoin I, right? It's a Gaussian integer. Same argument, essentially. It says that the norm of the unit has to be 1, right? Then all of a sudden, in the quadratic integers, you've got a squared plus b squared, which is the norm of u, right? If u is a unit, okay, equals 1 for u a unit, right? But geometrically, this is way different, right? Because if you look at the unit circle, which you can, right? It has 4 intersection points with the integer lattice. 1 in the complex plane, I, minus I, and minus 1. Those are all units of the Gaussian integers. It just so happens that the lattice of, lattice, oh man, I wish I had this notation. I'm going to use it anyway, be forgiven. So really the question for the units is, how does this line up? Z, direct sum, IZ. So that's kind of a, I could say that's what I've been calling Z2 before, but the Z2 inside C, I would say it's Z direct sum IZ. So like, you're looking at integer imaginary coordinates and integer real coordinates. And if we take Z adjoin some quadratic integer, the question is, like, where do those multiples line up with this grid? It so happens that with the Gaussian integers, we pick up these 4 units on the unit circle, right? So for a more general number system, the question is, how many of these new numbers fall on the unit circle, or in this case, that ellipse? Well, yeah. Well, I don't know. Where is that? It's still the unit circle. No, I'm going to shut up about that. I just think it's interesting to think about the question of what are the units in a given number system. You can disagree. That is your prerogative. Oh, man. Curses. It's okay. I'm going to keep going. So, if this doesn't work, what do? We give up on problems of 3? Or is there some other system of numbers which is helpful for studying questions which have a 3 in them? Right? show you how Stillwell presents the problem geometrically. He says if you picture z adjoin root minus 3, the trouble is if you look at like a triangle, he says you should look at a triangle formed by the shortest distance between 2 points in the grid, which would be this, right? So if I look at this, and I look at a triangle here, like that, if your rational number, excuse me, if you take the quotient of two things in here, right, if you take the quotient of two of these guys, what happens? You know, if I'm in this, if I'm, for example, if I'm like up here, or if I'm like here maybe, let's say, or here, I don't know. There are places where I'm farther away from the closest integer than I am, the closest quadratic integer than I am from what? Like the remainder, how to put in words. The thing I've just erased, I can't make less than 1, basically, the analog of it. So he says the solution then is to just add more points. So what you do, let's suppose this is 0. Maybe you guys have heard of this or not, I don't know. If I want to look at a unit circle, right, I can talk about the roots of unity on there. So in the complex exponential notation, it's e to the 2 pi I over n. So 1. So basically, if you look at e to the 2 pi I over n, and you raise it to the nth power, what do you get? Turns out you get e to the 2 pi I. I'm not proving these things, just telling you. And that's 1. Now, more generically speaking, e to the I theta is cosine theta plus I sine theta. And we really should tell you this in Calc 2. I think some of us probably did. I know I would. Tell you in Calculus 1. But that's because I'm misbehaved. So my point is, these are the so-called nth roots of unity. All right, so they appear every, you know, in terms of angle, 2 pi over n. Every 2 pi over n spacing around the unit circle, you get a root of unity. And so-called nth roots of unity. I mean, so for example, in the Gaussian integers, for Gaussian integers, you saw these roots of unity. You saw the fourth roots of unity for the Gaussian integers, right? For Gaussian integers, you had like this one, this one, this one, and this one, right? So like n equals 4. You're looking at like e to the 2 pi I over 4, which is what? E to the pi I over 2. What's that? That's cosine pi over 2 plus I times the sine of pi over 2. So what's that? That's just I. So the fourth root of unity is I. And so essentially he's just going to use the third root of unity to build the rest of what we're missing, okay? So, and he uses a notation. Let's see if I can draw it. So here's the definition. It's awful. I can't make this symbol worth anything. Squiggle 3, I guess it's C3, would be cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. So if I was to illustrate that, that would be, instead of pi over 2, it would be 2 pi over 3, so that's like over here. Awful. So if you look at the square of that, it's over here. And then the cube of it, it's back to 1 again. Because it's a third root of unity. That means when you cube it, you get back to unity, which is 1, right? Okay, so geometrically, like that's where, it's just a little background for you as to where this number is coming from. If you don't understand all that background, it doesn't really hurt you in here. In fact, all you really need to know for what I'm about to tell you is simply this, is that this funny looking 3, I'll call it C3, is nothing more than minus 1 plus I times what? Times the square root of 3 over 2. I mean, that's the Cartesian presentation of the third root of unity. It's a little bit negative, right? A little bit negative, and it's up root 3 over 2. So if I add that point, so like here's 0, right? These, you know, to be clear, this was I square root of 3, right? Here was 1 plus I root 3. This guy was what? 1. This one was minus 1. This one was minus 1 plus I root 3. What am I missing? So Stilwell says we're just missing these other points in between, midway point. So like this would just be that guy. And here's 1 plus that. And so centered around 0, you also have this one down here too, right? And you have this one. What are these points? See here. So if you go the other side of the origin, it's what? Minus what? Through the origin, right? It's minus C3. Now, to be more specific, it's 1 minus I squared root of 3 over 2. There's, you know, that's the actual value of that point. It's just convenient to use this C3 thing to, you know, have less writing. Now this would be minus 1 minus C3. Oh, my symbol is degenerating. At some point I'll learn how to write that thing fast. I just not yet. Oh, sorry. Oh, hey, check it out. What is the thing about all of these 6 points I just drew? Well, before I get to that, oh fine, I started it. What's this distance? 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 What's that distance? 1. Yeah, 1. All distance 1. So, and okay, so that's one thing. They're all distance 1. The other thing I would point out to you is that you can build the square root of 3 from the C3. How would you do it? Square root of 3 is equal to what in terms of C3? Can you? What do you got? You got 2 C3, right? Plus 1 divided by I. So if you work that out, what is that? That's what was C3 again? It was minus 1 plus I root 3 divided by 2 times 2 plus 1 divided by I. Let's see here, can I? What does that give us? Oh, I'm sorry. This is. I'm going to end up with like something like square root of 3 equals square root of 3, which is going to be useless here. Let me approach this more constructively. Sorry, guys. That's C3. This is oh, saw it when I wrote the notes really fast. This is why I write notes, right? What's C3 plus 1? If you add 1 to this, what do you get?
Plus I squared root 3.
Yeah, 1 plus I root 3 over 2. So you can see then from that 2 C3 plus 1 is equal to what? I squared root of 3, right? It's equal to the square root of minus 3. I would point out to you that what that means is if I adjoin C3 and I look at integer combinations of those, right? That means I will pick up, if I use this red point, if I look at like Z adjoin C3, I automatically pick up that, that includes what? That includes these guys. Because of this, right? I can build the square root of -3 from this third root of unity. I should call it the third root of unity. That's its name. Primitive third root of unity, actually. You with me? Maybe. I mean, I don't know why they're interesting, but you can hear the words coming out of my mouth, I think. Great. So in this newfangled set, Z adjoin third root of unity, which would be what? It would be A plus B third root of unity. Sorry for the abundance of notational versions of this I've written on the board today. I think it's become a 5 with a thing at the top now. It's the saddest one yet. Oh man. Anyway, pathetic. All right, so that is a set of quadratic. Oh, I said it's a set of quadratic integers, but I'm not sure about that. What equation does the third root of unity solve? It solves x cubed equal to 1, right? Which you could rewrite as x cubed minus 1 equals to 0. I'm claiming that this is a quadratic integer. It looks like maybe it's a cubic integer, right? Why isn't it a cubic integer?
So you can factor that into x minus 1 times x squared plus x plus 1.
X squared plus x plus 1, you say?
Right, and it's not 1, so it's a solution to x squared plus x plus 1 equals 0.
Right, right. So it solves this. Third root of unity solves this. That's actually geometrically fun to think about. So this guy down here, by the way, this minus 1 plus C3 is actually the third root of unity squared. So if I take the third root of unity squared, which is this point, and then I add it to that point, what I get, the imaginary parts cancel, and I've got like a real part of minus a half, a real part of minus a half. So I get over here. So this plus this gives me minus 1, but then minus 1 plus 1 gives me 0. Kind of fun geometrically to think about why the third root of unity solves that quadratic. But it is in fact a quadratic integer. Okay. My claim then, guys, is that this third root of unity, Z adjoin the third root of unity, this new set of quadratic integers, in fact, does have the division property. I haven't showed you explicitly like that Z adjoin square root of 3 doesn't have the division property. I just showed you some poisonous fruit from the fact that the division property fails, right? I'm claiming over here that the lack of unique prime factorization, it's an indicator, right? Because we know if we had the division property, then we could prove Euclidean algorithm, then we could prove the Zhao's identity, then we could prove the prime divisor property, and then we can prove the unique factorization. That was the structure of the logic earlier in the course. And the fact that we don't have unique prime factorization goes to show you that the division property fails for Z adjoin root minus 3. Now, what do you think the argument's going to be that the division property works here? I've got to do it today, otherwise it's just wrong. That's probably all we'll get to today. So if you look at your fundamental triangle, right? Basically, pick A plus B's third root of unity, C plus D third root of unity, element of Z adjoin third root of unity, right? And then form their quotient. Let this be Z, let this be W, which is not equal to 0. Look at Z over W, right? That's going to give us something in the the rational adjoin the third root of unity, right? And so if you look at the fundamental triangle, it's something like what? It's something like M plus N third root of unity. What are the other points in this thing? this one's the other easy one, m plus 1, right? Plus n, third root unity, right? If I give this thing a name, if I call this quotient alpha, it's got to be somewhere in here, right? I mean, if you think about taking the quotient of these two complex numbers, this triangle, the set of triangles that fills the complex plane, it's got to be that complex number is inside some one of these triangles. And if I just label the lower corner by m plus n times the third root unity, I can figure out what are the other corners. What are the other corners here? M plus 1, right? What's this one up here? To get from 0 up to here, I did what? I added 1 to the real part and 1 copy of the third root of unity. So it's actually m plus 1 plus n plus 1 third root of unity. The point here then is if you take the quotient of two such numbers, you can look at you can put a bound on the distance. What's the largest distance you could have here? No, 2/3. Is what you said 2/3?
No, it's not 2/3. It's like
not
square root of 3 over 3.
Square root of 3. Let me see here. So this, I'm not sure exactly. This is 60 degrees though, right? No, 30 degrees. This distance down here is what? It's a half. So that makes this what? Well, I guess I just want to figure out what the hypotenuse is, right? So what can I use? I could use cosine. What? Cosine 30 degrees is equal to 1/2 over the distance I want to know. So the distance is equal to cosine of 30 degrees over half. That's the worst case scenario. Cosine of 30 degrees is what? Square root of 3 over 2, right? So this is square root of 3 over 2 over 2. Oh man.
3.
Hey, it's square root of 3. What?
It's 1/2 over cosine of 30.
Oh yeah.
Sadness.
Yeah, I can't do that. D is equal to 1/2 over cosine of 30, right? So 1/2 over the square root of 3. So in fact 1 over root 3, right? So you just basically, if alpha is pictured, you choose, you let mu equal to the closest vertex, right? And then you can see that z over w minus mu is less than 1 over 3. And then, etc., get division property. I have the gory details written in the notes, but I think you guys, you don't need to see me do this argument again. I don't think it's the same argument we go through. You start with what we want, which is that the size of the remainder is less than the size of the dividing number, right? That same list of equivalencies goes through. It ends up being that you just need the condition that the distance to the closest integer point on the lattice is less than 1. So basically, whatever you're building these quadratic integers from, if they form some sort of like tiling, let's say, some sort of repeating pattern in the complex plane, as long as if you pick a typical point in the typical cell, as long as the distance from that point to the closest integer is less than 1, that is a sufficient condition geometrically to get the division property. That condition fails when we just have square root of minus 3, because you can pick points in a cell which has like this. You can pick points where the closest point is further than, like the center point, right? How far is that from these corners? If this is 0, this is square root of minus 3. How far is this? So here you got square root of 3 over 2. Here you got 1/2. Yeah, that actually is distance 1, right? and that's why it fails. It's too far. So you have to fill in the holes by joining the square root of -3. These, by the way, have a name. These are called Eisenstein. So I'll probably spend Eisenstein. I'll spend a little bit more time on these next time, but I think we'll be more or less back on track with the schedule come Thursdays, by supposing we don't have snow and stuff.
What does that say?
Eisenstein. Not Einstein, kind of like Einstein, but the next is an extra syllable. So hopefully, by third day, I'll be talking about quaternions. And then after break, I'm hoping to jump over to quadratic reciprocity.